What? Can Mambo labs be out?
When will Mambo labs be out for everyone?
Not for everyone. I'm gonna do those labs in class. Mambo labs. And then basically I would assign those as tasks. So what you will do, for an example, today I have assigned the lab, right? That is for 2 points. So in next class, I will do a small demonstration of Mambo in class. And then I will ask you to repeat that demonstration on your own at home and upload maybe a video or a picture for say 1 point. So please understand, at this point, if you want, you can score 92% of the final grade, right? So for remaining 8, it will be like sort of hands-on activities. And you know what? I was feeling super generous. And some students say, hey, this is too tough for me. I'm not able to do with Telo and all that. So I'm going to give you a project for 20 points bonus on top of everything. And even though we don't have plus and minus grading, if you score more than 110 in the course, I will give you A plus. Okay. What?
When are you releasing that?
Of course. Tonight. How does that sound? But that project is optional and that project is difficult. So no pain, no gain. And the only reason I wanted to give this project because in case if you have had issues with programming, if you say that Telo labs are too difficult, my drone broke, my cat died, my Telo hit my cat and cat died, then I cannot fly Telo in my neighborhood. So that's why I want to give you one more project, which is bonus. And that would be on robot learning. So basically you would do the Coursera course on robot learning, upload all the assignments. And if you do that, you will get 20 points bonus on top of everything. Happy? Okay. Okay. So in today's class, I'm going to talk about observability. Then we'll talk about Kalman filtering. We'll briefly touch upon multi-rate Kalman filter. We will talk about extended Kalman filter. And at the end, there will be a lab activity. And why Kalman filtering is super important? If you have started looking at the perception course on Coursera, it talks about Kalman filtering. It talks about combining different sensors and coming up with meaningful data. Oh, something I want to tell you before I forget. This summer, I'm teaching EGR456 Mechatronic Systems class. So if you are interested, please take that course, because what I'm going to do is in that course, I'm going to build a drone from scratch. So basically using 550 in summer. So basically remember the knob that I showed you in last class, wherein you go by step by step by step by step. So what I'm going to do is I'm going to build a drone, flying drone with a frame and Arduino, program the Arduino with the custom firmware, and then have that drone either do path following or it can do interface with GPS and so on. That will bring back my memories when I was working on Arduino pilot. So I would share my code with you, and we will, if you guys are interested, that would be the project that we will do in EGR456 mechatronic system class in summer. Yeah. We are building it in class. So basically what we will do is we'll get the small motors, we will get the small Arduino Nano, we'll get transistors to control the speed of the motors, and then actually custom firmware and add the GPS module. and then it will do the stabilization. It's a lot of fun. Yeah.
Yeah, 4+1.
You can take four. Seniors can take it.
No.
Well, we're not
4+4 is
seniors.
accelerator.
We're some of us are juniors.
Huh?
Some
No,
of
but
us
you'll be senior next year, right?
Not from next semester.
next year.
Just talk to the advisor.
4+1 can take it, and advisors can do advising override.
Yeah.
If you talk to them.
So just talk to your advisor, and if so, let me tell you, if you have taken robotics systems too, you should not have any problem in doing mechatronic systems EGR456. Just talk to advising. That course is approved for other concentrations as well. So if you are looking for, if you are in MS robotics, the systems engineering concentration or some other concentration, you are welcome to take that course. Especially if you have taken robotics too. I was looking at it, and then all of a sudden I found out all my autopilot codes and all. So I thought, why not to actually, as a mechatronic systems, why not to build a quadcopter and fly it? Question? No. But you can sit through the class if you are interested. You can. I would be offering that course via Zoom as well, so you can listen to the course, and then you can do the project on your own. Basically, we'll build a drone in $20. So yeah, you can build a drone in $20. When I started, it was super expensive, but nowadays you can build it very cheaply. Yeah.
How can we get the
Zoom link? Yeah, shoot me an email and I will send you the Zoom link. Any other questions? Okay. So, first and foremost question is observability. How can you observe something? By patience and persistence. So what that means is, for example, if someone is sick or not, for that we check the pulse. And by checking the pulse, you can kind of deduce if that person is alive or dead, or sick or healthy. You actually measure the temperature. So you should be able to observe, to conclude, or to infer about the state of the system. And that information could be available to you directly, or that information could be available to you indirectly. What do we mean by directly available information? For an example, if you find the position, that information is available to you directly. But if you want to derive the velocity from that position, if you know the time steps, you can divide the change in the position by change in time, and you can find the velocity. So sometimes if you want to find out a variable, you directly have access to the variable, or you may not have the direct access to variable. That is where the observability comes in the picture. So what is the definition of observability? Observability means you have the state. That state has certain input, and the state changes because of input. And what you do is you find out the response of the system and try to estimate or try to identify where that system is. So for an example, if they give you the velocity, you try to find out what the position is. If they give you the acceleration, you try to find out the velocity. By integration, double integration, you can find the displacement. Now, at very minimum, this is the standard form of the continuous time differential equation system. This is the first order representation that we studied in robotics 1, where x dot is the first derivative of state. A is the constant matrix. X is the state. B is the weights on the control input, and U is the control input. And Y is nothing but the observation, and that observation is somehow related with the state by matrix C. So please understand, when we talk about observability, that matrix C plays a critical role. Now, in the next few slides, I'm going to show you some examples of practical system where you can observe the system and you cannot observe the system. So what is the definition of observability? Now, I want you to understand something like this. You know y. Basically, y is given to you. So given y, we have to find x. So how do we find that out? So y is equal to c transpose x. If you take the derivative, you get y dot is equal to c transpose x dot. But what is x dot? Please understand, from this equation, x dot is equal to ax plus bu, which means when you substitute this equation in here, and if you repeat the process, you are gonna get a linear matrix equation. In that linear matrix equation, that matrix equation is solvable as long as this matrix has a full rank. What I mean by that? I will start with a very simple example. 2 oranges plus 1 apple is equal to $6. 4 oranges plus 2 apples is equal to $12. So from here, can you tell me what is the cost of orange and what is the cost of apple? No, because there are two unknowns, or cost of orange and cost of apple, but there is only one equation. Do you agree with me? What that means is, I want you to understand, if I write this equation in the matrix form, remember linear algebra, OR and A, if you find the rank of this matrix, rank is going to be 1, but there are 2 rows. So this matrix is rank deficient. And what that means is these variables cannot be found out. I want you to think about the same logic over there. What you have is, you have all these y's, okay, all these y's, y dots, and you have all these x's, and you have that matrix C transpose A, that matrix that is over here. If this matrix is not full rank, if this matrix is rank deficient, you will not be able to find out the values of x from y. Everyone understood this? Don't believe me? I'm going to show you a practical example, and then I'm going to show you a video that will actually make these concepts clear. So this is the basic theorem. The system x dot ax plus bu and y is equal to c transpose x. A is observable if and only if that observability matrix, that the matrix that is a transpose a square, that matrix has the full rank. Now let's look at an example. So this is a very classic example that is motivating for Kalman filtering and sensor fusion. And this is the example that we will see in the videos. Say for an example, if you have an inertial measurement unit which has accelerometer and you have a GPS. So basically the GPS is going to give you the position estimate. GPS will tell you where you are. The inertial measurement unit will give you acceleration. You integrate the acceleration and you'll get velocity. But the output from the inertial measurement unit is noisy. So how do you combine these two measurements, basically the GPS and an accelerometer, to get an estimate? And please note, this is not the true measurement, but this is an estimate for the speed of a car moving in one dimension. So for that, basically the GPS receiver is going to give us the equation for position. And the very simple model is P dot is equal to 0100 P, and V dot is equal to, you have 0 V, and you have some type of noise in that measurement. Now the question is this system observable? And the answer to that question is yes. And let me try to tell you what this means. From GPS receiver, let me give you a very practical example. From GPS receiver, you know the position. Do you agree with me? You know the timestamp. After some time, from the GPS receiver, you know the position, you know the timestamp. Do you agree with me? So you have two positions and two timestamps. Can you find the velocity? You can find the velocity. You agree with me? Okay. So that's what this equation tells you, that this means that the system is fully observable. Now here is the another problem is, now you are trying to do the exact same thing with accelerometer. And I want you to understand that you are trying to do the exact same thing from accelerometer. And from accelerometer, what we are getting is, we are getting total acceleration and time at one point. Then you are getting total acceleration and time at the other point. You may say, I can, so this is very important, I can integrate and find the velocity. But this is very important. When you integrate, one important piece of missing puzzle is the constant of integration. Do you agree with me? If you are going to find out the velocity based on acceleration at time t1, acceleration at time t2, what would you do? You would find the difference in the acceleration, multiply by the time step, and that will give you the relative change in the velocity. Do you agree with me? But you don't know the initial velocity, which means you don't know what was the velocity of the vehicle when the velocity started. You have change in the velocity. You have change in the velocity, but you don't have the initial velocity, which means you cannot find out the total velocity accurately, which means the system is not observable. Everyone understood this? So from GPS, so derivative, so that's why many a times what you do is you take the sensor reading and then define the derivative, because when you decide to do integration, you need to know the constant of integration that may or may not be known. So another example is, you have the accelerometer on these two balls, and these two balls fall down, and then can you find out the speed of these two balls? So the idea is, unless you know the initial velocity, you don't know the constant, then you cannot find the actual speed of this red ball, ball 1 and ball 2. So that is an important observation for observability. If you take linear systems class, they will talk a lot. There will be at least 5 to 6 lectures on controllability and observability. But try to understand, observability means given certain value, given certain observation, can you find the state? That is what the observability means. So, and many a times the systems are observable, many a times systems are not observable. Everyone understood this? My online students, any questions? Okay, now comes the next part. Once again, a big caution. If you have not seen Kalman filter before, this material is going to look very alien. Unfortunately, if the Kalman filter is discussed just by equation, it's super complex because it uses Ito calculus, if you want to, which is the stochastic calculus. but in principle, the ideas are super simple. Fundamentally, we are trying to find out an estimate of certain value. And so for again, the idea is if you have a noisy signal, how do we find out from that noisy signal what is the best possible estimate? What is the best possible true value? It may not be the exact or accurate true value, but what is the best possible true value? So what happens is, say you have, again, the example is you have IMU, which is giving you accelerations. You have GPS that is giving you positions. IMU is very noisy. GPS is also very noisy. How do you combine these two noisy measurements and still find a good, accurate estimate? So for that, you have the concept which is called as unbiased estimate, which is the expected value of the estimation. And you have the minimum variance estimate. You have something called as the minimum variance estimate, which is uh, the minimize the spread and run that through some type of optimization criteria, some cost function. If you open a book on Kalman filter, you will see equations after equations, equations after equations for 5 to 6 pages of equations. So first you are going to see the true model. Then you are going to see the model description. Then you will see some matrix that deals with covariance. Then you will talk about the estimator. Then you will talk about the minimization. And finally, you are going to get this equation. This is the heart of the Kalman filter equation. This equation is that new value is equal to the previous value multiplied by a gain multiplied by the difference in the observation. I will repeat this once again. So this is the state update. This is the previous state. This is the difference in the observation multiplied by a tunable gain. So what does that mean? For an example, there I have a previous estimate and I get an update. I have a previous estimate, I get an update. If I trust the update, then what I'm going to do is my weight towards the update will be more. So I will trust the update more. And what that means is this tunable gain will be going towards the innovation or the difference. So what happens is in every iteration, it is sort of a back and forth process, where in every iteration, the Kalman gain is updated and this equation is recursively calculated. And trust me, I taught Kalman filter multiple times, and it is difficult, honestly, to kind of get the feel for the mathematics of Kalman filter. So what I'm going to do is I'm going to sit back, relax, and play a movie.
In this video, we'll discuss why you use comments. If you're not familiar with the topic, you may be asking yourself, what is a comma filter? Is it in your random copy filter that forces the spacing copy? No, it's not. Comma filter is an
What happened?
optimizational algorithm. Today we'll discuss two examples that demonstrate.
Just a second. I need to change some settings on the Zoom. And hopefully, I will play this video. Okay, my online students, can you see this video?
Today we'll discuss two examples that demonstrate how to use the comma rules. In the first example, we will see how can be used to estimate the system state when it cannot be measured directly. To illustrate this, let's go to Mars before anyone else does. If your spacecraft's engine can burn fuel at a high enough temperature, you'll create thrust that will let you fly to Mars. Finally, according to NASA, liquid hydrogen is a light and powerful rocket propellant that burns with extreme intensity to 500 degrees Fahrenheit. But be careful because if too high temperature can put the mechanical components of the engine at risk. And this can lead to the failure of some of the mechanical parts. If that happens, you might be stuck in your small spacecraft, very crafty for use. To avoid such a situation, you should closely monitor the internal temperature of the combustion chamber. This is one of the tasks since a sensor placed inside the chamber is met. Instead, it needs to be placed on a cooler surface close to the chamber. The problem you're facing here is that you want to measure internal temperature. Instead, you have to measure surface. In this situation, you can use a Kalman Filter, find the best estimate of the internal temperature indirectly. This way, you will extract the information about what you can't measure. Now that you know the solution to a problem, you can consider but are you scared? Let me tell you this. For Mars, you're going to weigh 62% less than you weigh on Earth. So let's go less. Okay, now let's go back and take a look at another scenario that takes place on Earth. In this example, we're going to see how the Kalman Filter can be used to estimate the state of the system by combining measurements from different sources that may not work to know. You have guests returning from overseas, pick them up from the airport. You're using your car's navigation system. Let's look at the sensors you have on board, which help you find your position and navigate to the airport. In order to measure units, uses accelerometers and gyroscopes to measure the car's acceleration and velocity. The velocity measures the distance covered by the car. The GPS receiver is sequence from satellites locate the car on Earth's surface. The rapid power for the vehicle, a very, very long power. And in the tunnel, it gets harder to estimate the position through GPS, since the receiver's line of sight to satellites is blocked and GPS simulated. In this case, we may cross the IMU limits, which means the acceleration. However, doesn't tell you much about the car's position. For that, you need to take a doubling catalog. This operation is complicated. Small errors accumulated over time. To get better position estimates, you can use IMU measurements along with odometer. But note that odometer measurements can be affected by the tire pressure and road conditions. Sometimes, your sensors measure the relative position. You can test something, but they are formidable. GPS receiver provides the absolute location, but it gets updated less frequently than it. In this scenario, the Kalman Filter can be used to extreme measurements to find the optimal estimate at positions. Let's look at some facts about Kalman Filter. Kalman Filter is the primary role of the field. It is an optimal estimation algorithm that predicts a parameter of interest, but expectations in a fraction in noise and weather. Kalman Filter includes guidance navigation systems, computer vision systems, and signal processing. One of the first applications of Kalman Filter was in the 1960s. Behind guesses as to what it helped with, engineers use it in the Apollo project, where the Kalman Filter is to estimate trajectories of the manned spacecraft to the moon and back. That's what we've seen. Filters are used to optimize variables of interest in the can't-be number correctly, that measurements available. They are also used to find the best estimate of space by combining measurements from various gases in the presence of noise. In the next few years, we'll cover what Kalman filters are and how they work. Kalman filtering is the method to design optimal state observers. And for the next video, we'll learn state observers, and our discussion with optimal state estimators.
So, the first video kind of gives you an overview of what Kalman. So, what Kalman filters are. So, before we move on to the next video,
This is the doctrine, and you want to know what he's doing, how he's treating. However, there is no
any questions on what Kalman filters are? Everyone clear about the use of Kalman filter? So next part is the observation or concept of observability. That is the video.
direct way of measuring physics. So what you do is, quickly, start observing the statement. This observation helps to estimate the real moon. State observation helps to estimate something that you can't see or measure directly. Throughout the rest of the discussion, if we see something with a head on it, which means that it is estimated through a single observer. So if the state X is shown with a head, then it's an estimate. Next, we'll look at a more solid example. The traveling in space is traveling with planets. In order to get to the planet system, we need to show the temperature. If it gets too hot, it will damage your spacecraft. However, there is an way of measuring the internal temperature, since the sensor plays inside the engine. Now, what we can do is to place a sensor on a colder surface and measure the temperature there. That's called as temperature T1. And the one we can't measure, but we need to. This is the 1.05 since this will happen regular and truthful. Access to this. Signals that are relevant to you are the truthful and observable. Now access to your information. You always know how to correct it. So if you don't think it was truthful for the medical market, and also, not all the relevant equipment. Okay, now this story. No, it's good at math, but in reality, the mathematical model we found is not very logical. The real system is the model of the sequence of conditions values with match. Therefore, the estimating but in real life, external temperature, remember, that's why you need to use the same estimator to estimate your internal state. Let's see how it differs. Here, all the external temperature, we know that it is warm. That's a positive temperature. So the estimated temperature will cover to minimize the difference between the estimate and the external temperature. That's the sound. Actually, talking about error, the method and estimate for zero. That's part of the system. How do you control it? You know how much you can run this estimate the output, which is the okay. Look for more insight. Where will discuss your findings.
Okay, for online students, if you are not able to watch this, I don't know what the issue is. I'll just, you can click on the link, and I'm putting the link in the chat window. Now, did you understand the concept here? What is happening is you have a mathematical model and you have an observation model. And what we are trying to do is basically minimize the error between the mathematical output and the observation. And that is error in the observation. And please try to understand that finally becomes sort of a control system equation. If you adjust the gain, then you can tune the gain in such a way that the measurement of what you're observing matches with the output of the model. And that is the crux of observation. And that is basically this equation is all about.
In the next video, we're going to start into
What? Yeah. What? No, so all that error function is done to find out the optimal value of k. So in every iteration, the value of k is changed. And if you look at the whole math behind it, what you need is you need to find out the value of phi. Kalman filter mathematics is a little bit too much at undergraduate level. Kalman filter is okay for graduate level, but please understand, Kalman filter is the crux of navigation, tracking, machine vision, all those types of algorithm. So I would, if you like, I can play these videos, and I would very much would like to, I want you to watch these videos, like what is optimal state estimator and optimal state estimation filters. You want me to run these videos, or you'll watch those on your own?
Personally, I think you can watch them.
But this topic is super important because next lab, okay, the next part is, this is the crux. You have the estimation from one module sensor, you have estimation, you have measurements, and how do you take these two noisy processes and decrease the variance? Kalman filtering is a linear approach, wherein that means the system is linear. What happens if the system is non-linear? And when the system is non-linear, what you do is you kind of perform the linearization at each step. So when you perform the linearization each step, what you get is you get something called as the extended Kalman filter. And in extended Kalman filter, you have a Taylor series expansion that actually does the linearization. And then if you look at the equations for extended Kalman filter, those are even scarier than the regular Kalman filter. And please note that again, don't let these equations scare you. There are excellent movies, part 5, part 6, and part 7, that I would encourage you to do that. Just watch those videos, and it will give you a very nice, intuitive, graphical explanation of what Kalman filter is. I can derive the mathematical equations of Kalman filter, but to be honest with you, we are not going to write our own code. In the MATLAB, there is a Kalman filter block. We are going to grab that block. We are going to feed the inputs to that block, and that block will find the optimal estimate. So we are not going to see how it's working under the hood, but I want you to have a decent understanding of the mathematics of what Kalman filter is, how that Kalman filter works, and everything. I also recorded an excellent webinar on Kalman filter for my robotics 2 class students. So I would also add the link to that. But these webinars are much, much nicer than the webinar that I did. So what I want to do now is, in the last part of the lesson, I want us to do this Kalman filter lab. So online students, what we are going to do in next 15 minutes or so is, I want us to do the labs. So please go to please download the lab, go to modules, and in modules you can actually download the Kalman filter lab, and then open the Kalman filter lab. Open the Kalman filter lab. And in Kalman Filter Lab, right click and then open with MATLAB 2021B. And this gives you a virtual lab for the Kalman filter. And what I want you to do is, I want you to read this and then step by step do this activity. Part 1 is to simulate a simple pendulum and visualize its swing motion. Then basically compare it to the actual pendulum and then design a Kalman filter to estimate the angular position of the pendulum. And the last activity is the design an extended Kalman filter to estimate the angular position of a nonlinear pendulum system. So please go through this lab activity. That virtual pendulum model SLX is in models. So basically virtual pendulum model SLX, this pendulum is in the models. So you can use that model and then add the blocks to it and then do part 1, do part 2, do part 3, and finally you can do the part 4. And assuming that you do these 4 parts, it's actually a very well written lab activity that will make you very comfortable with Kalman filter, application of Kalman filter, like where you would use the Kalman filter. So please start this lab activity. If you have any questions, you can ask me. Online students, please work on this lab activity. If you have any questions, you are welcome to use the chat window. Oh, did I? No, it's on. Yeah. So use chat window, or you can stop and ask me questions. So this would be the good time to start the lab activity. And I'm going to stop recording.